Okay, so let's start today's class. So I have uploaded the slides, and you should also receive my message from the NTU email. NCC email, sorry. Yeah. So today we will introduce a second identification strategy called matching methods. And then we will also discuss how to use data to examine your data set and also how to create the sample for your analysis. Okay. So matching methods. So from the last week, we learned our first identification strategy to identify the causal effect. That is the randomized control trial, RCT. And RCT is, you can consider, is the golden standard so it's the best identification strategy for the causal inference. Because the causal inference is trying to help us to identify causal effect and using the observed data. But when you use observed data, you usually will mix with the causal effect and the selection bias. And the selection bias basically comes from the facts that individual can choose whether they can get treatment or not. And this decision or this behavior is related to a lot of confounding factor, like ability, family background, or age, or other things. So you cannot just simply compare the outcome for those who get a treatment and the outcome for those who decide not to get a treatment. It will always give you selection bias. But if you use the randomized control trial, you can basically eliminate selection bias due to several features. One feature is when you do a randomized control trial, the researcher can determine who can get a treatment or who cannot get a treatment. So basically, the individual cannot choose, I want to get treatment or not. And also, how the researcher assign the treatment is based on random process. So who get a treatment is random. It's unrelated to any factors. It's not because you are rich, you are more likely to get a treatment, or you are poor, you cannot get a treatment. It's just due to the random process. So due to this, it will make the treatment status is unrelated to any observed and also unobserved factors. And then we can basically eliminate selection bias and make the treatment group and control group now will be very similar in terms of all characteristics. So that means they are comparable. So the only difference is treatment group get a treatment and control group did not get a treatment. So if we find any change in the outcome, we can attribute to the treatment status. Okay. But in the social science, it's very hard to implement this randomized control trial. Basically, usually it's only in the life science or nature science we can use a randomized control trial. In social science, implementing randomized control trial is very expensive and sometimes has ethical issue because you cannot force a human or an individual to do something he didn't want to do. Okay. So for example, you randomly assign a master's degree. So what about those who do not get a master's degree? You cannot do that. So basically you cannot implement randomized control trial to answer very important question. Only if you find some very smart way, like last week we have discussed several researchers, they use randomized control experiment, but they find some creative way to implement this and answer big questions. But typically, it's really hard to do that. So in the social science, many empirical studies, they basically cannot use experiment to get a causal effect. We usually use non-experimental data to to estimate the causal effect. And so we all usually call this type of empirical research is as the observational studies, because researcher can only observe who can get a treatment, who do not get a treatment. We cannot decide who can get treatment or not. We just observe. So we kind of like an observer to see who get a treatment, who do not get a treatment. But we cannot assign a treatment like we do in the randomized control experiment. Okay, so that's the typical case in social science.
Professor, like with observational study, so because we don't assign the treatment, like if it's a natural experiment, like something that happens because of a policy.
Yes, that's another strategy you will learn in the later class, like difference in difference or regression discontinuity design, that usually use some policy change or some institutional detail to create the nature experiment. Yeah. Okay, any other questions? Okay. But it also belong to the observational studies, because in that case, the individual still can choose who he want to get treatment or not. Yeah. The researcher does not really assign a treatment like randomized control trial. Okay. So you need use more methods or more strong assumption to claim you can get a causal effect. Okay. So in contrast to the RCT, in observational studies, the researcher basically cannot control the assignment of treatment. We cannot determine who get a treatment and who cannot get a treatment. We can just observe. So the only thing we can do is we can try our best to make treatment group and control group, their observed variable are similar. Try to control for the observed variable. For example, make the treatment group and control group, they have very similar age, very similar family background, something like this. Or use some indirect method to adjust unobserved variables, like personality or ability, something like this. And you will learn several methods that can use direct way to do that, like a policy change, as she said. We can use another method to do that. But today we will not discuss that kind of method. So the goal is try to make other things equal between the treatment group and control group in terms of observed and unobserved variable. Okay. And so we try to make the only difference between treatment group and control group is treatment status itself. So the goal is we try to design the observational study to approximate the randomized experiment. That's our goal. So today I introduced the second identification strategy you will learn in this class is so-called the matching method. So the main idea of matching method, or the key assumption of matching method, is we assume all confounding factors are observed to the researchers. But you can consider this is a very strong assumption, because a lot of confounding factors that might affect who get a treatment, who cannot get a treatment, and also their outcome. Such confounding factor could be unobserved. Personality, or your preference, something like this is unobserved. But in this method, we assume all are observed. So based on this assumption, we can claim we can get the causal effect. But you should pay attention, it's all based on this assumption. So maybe in some situations it's not very realistic. So in that case, maybe you cannot make very strong claim for you really get a causal effect. But you just need to understand the assumption. Okay. So given this assumption, matching method is a way to eliminate selection bias, because all the confounding factor can be observed, can be controlled. then we can just construct a control group of the untreated units with the same characteristics with the same as the treatment group. So basically, we can construct a control group with the same characteristics, and the treatment group have the similar characteristics, because all characteristics based on these assumptions can be observed. Okay. So after controlling the observed covariates, we can identify the causal effect by this assumption. Okay. So you should always know the identification strategy is always based on assumption, and under this assumption, we can get a causal effect. But some identification strategy is based on more reasonable assumption in some situation, and some identification strategy may be based on more strong assumption or more restrict assumptions. So that's when we evaluate which identification strategy is good or not. That's basically based on their assumption. Okay. So any questions for this? Okay. So this can accomplish by match the treatment group and control group. Try to make they have the same characteristics. So for example, here we use an example that maybe we want to estimate the causal effect of job training program on workers' earning. So when people get unemployed, they try to find a new job, so they can participate in some job training program. So we want to know whether those who join the job training program, whether they can get higher wage or not. But if you simply compare those who join the job training program or those who not join the job training program, their wage could be not comparable, because these two groups are very different in terms of many things. Okay. So here we suppose the only difference between treatment group and control group is age. It's the only confounding factor that might affect why you join the job training program and also your wage. So you can imagine older people might more likely to join the job training program because they have more need to increase their wage, something like this. Okay. So here is an example. This is the example. So based on this example, we compare those who decide to join the job training program and those who decide not to join the job training program for these two groups of people. And if you simply compare those who join the job training program and those who decide not to join the job training program, their average earning, you will find those who join the job training programs, they earn less than those who decide not to join the job training program. So can we say the job training program is useless? We cannot really say that, because in terms of other characteristics, they are also not very similar. For example, the age. And here we assume the only difference is age. That's our assumption. So you can see, for those who not join job training program, they are older than those decide join the program. Okay, and it could be because so that's why they earn more, because they are older, so they have more experience. So we need to construct another sample that are more comparable to our treatment group, the those who decide to join the job training program, that make their average age is also 28.5. Okay. So that's the construction of the matching. So that's why this method called matching, because we choose some people from here to match the individual in our treatment group. So for example, we want to who can match with this unit 1, the age 28. So it's not this guy, 43. The age is quite different. So that means more comparable individual is those who are 28. that is this guy. So this guy will become our new control group to match this treatment group instead of using this guy, because this guy is older than this guy. Okay. And then you do the same process, try to find some people in the control group that with the same age as the treatment group, like 24, that is this guy. So you use that as the control group. And you do this process several times, try to match 29, this guy, to construct the more comparable control group. Then you do the same process over time, and sometimes you might find there are two guys within the control group have the same age as the treatment group. So in that case, you just take the average of their earnings. Okay, sometimes like this. Or three guys, you can take average for over these three people. And doing this, you can construct more reasonable control group like this, match sample. And this give you the same average age as the treatment group. And since you assume the only difference between treatment group and control group is age, basically other things are equal, so you can claim the difference in the earning between treatment group and this match control group. The difference is due to the job training program. Okay, so after you do match, this is before matching their age distribution. And after you do matching, like I just said before, you match each individual's age in the treatment group. You get exactly the same distribution in terms of age between the treatment group and the control group. And your results are different. Before matching, since the control group they are older, so the average earnings are higher than the treatment group. So you will get a conclusion that the job training program will just reduce your earnings. But this is because the control group tend to be old people. So after you adjust the age factors, the difference becomes positive. Okay, so you will get different conclusion. So that's the matching practically how we do. Okay. So any questions? Okay. You have question? No. Okay.
The only difference between the control and non-control group is we assume just between
in this case, it assumes age, but in reality, maybe not. Yeah, maybe they are very, very different. So in the reality, you might need to match other factors, not only age or family wealth, family income, or father's education, other things.
So this is just a simple.
Yeah, that's just I can show this in a table. If they have other dimensions are also different, you can see there are a lot of combination. So, but we will discuss how to solve this high dimensional problem, because treatment group and control group could be very different in terms of 10 variables. So how can we deal with such issue? How can we find the control group similar in terms of all these 10 variables is the issue we will discuss later. Okay. So any questions?
Like the unit 8% several times, is it okay to do that?
Sorry? 8%?
The unit 8%.
Okay. Unit 8, this one.
On the third column, it's used multiple times.
Yeah, it's used multiple times. Why can't
Oh,
you do that?
okay. Yeah, you can do that. But that's so-called whether you allow replacement or not. So sometimes you say your matching method does not allow replacement. That means you cannot use the same individual multiple times. Okay, but you can also do replacement. Yeah. So just claim what kind method you use. Okay. That's different method
But
too.
in that case, like we cannot compare without doing the matching because, or it's okay to do it like we're doing 19 in the first column with 21 in the second one. So that means that we'll change everything because we have much more participants in the second one than in the first one. So the average will change. We remove the last two, we have 19.
Oh, you mean
Yeah,
if
yeah,
you
so that
remove
makes it
this, you say we cannot find a matching.
like in the first two. Like we
Yeah,
can-
yeah, you are right. This
Yeah,
is
so-
the example I create for
Right.
teaching. So it's not always we can find exactly the
Without
same age. Yeah, it's hard. Yeah, but the point is we try to make the characteristic close as possible. Yeah, to the treatment group's characteristics.
So if we don't find a match in our sample, like if we're doing a project, how do we report it? Like, do we state like in our assignment for the final project for this?
Yeah, yeah.
Do we say that after collecting the sample, we put, like I just for example using the matching method. After collecting some samples, we couldn't find matches for units X, Y, Z, and then we discard them or
Yeah. If that means some characteristics, for example, age 28 only exists in the treatment group, not in control group. That means you cannot match. Basically, you cannot really use this method because you don't find anything. Any individual can help you to create a match sample.
also
Yeah.
for the matching method, all the in the treatment groups and all the ones in the control groups have to have a match.
Yes, yes,
Oh.
yes, yes. But you will learn other method, for example, called propensity method. This is we just match propensity, and this propensity basically summarize a lot of characteristics. Their effects. Okay, but you will learn this later. So basically, it's not exact. You need to use the same age. Later, you will learn. You just reduce the dimension to one variable called propensity score.
I guess you kind of answered it because I read a paper recently, and then they used the matching method, but instead of like 19 participant subjects, there were like hundreds of thousands. So it wouldn't be like individually matching one, right? It would be like you said, a propensity or
Score, yeah. In the practice, people might use propensity score rather than match each characteristic. Because here I just use one variable, one characteristic. You can find the procedure is quite messy. But if you have 2, 3, you have a lot of dimensions. Yeah. Any other questions? Okay. Good. Okay, so I use again the potential outcome framework to let you know what kind of causal effects we can identify using the matching methods. Okay. And here I would like to let you know the key assumption for the matching method. Why the matching method can let you claim you get a causal effect. It's based on this conditional independence assumption. So this basically is say, given you treatment group and control group have the same observed characteristics. For example, you all compare the people who are age 40, for example. Then you can claim who get a treatment or not is not depends on their value of potential outcome. So it's kind of like the treatment status is unrelated to your value of your potential outcome. It's kind of like random. Okay. So it's not because you have higher earnings if you go to grade school, you tend to go to grade school. So in that case, whether you get a treatment or not is unrelated to the value of potential outcome. If you compare the people who have the same observed characteristics. For example, you all compare those people are 40 years old. Okay. So in that case, we can use this assumption to get the causal effect. You will see later. And this assumption also called selection unobservable. This means basically we just observe who get a treatment or not. So that's why they say selection unobservable. It's because whether you get a treatment or not is just based on the observed characteristics. Okay, so it's because you are older, so that's why you join the job training program, and then you earn more, something like this. So after you control the age, the treatment group and control group now will be comparable. Okay. So any question for this? Okay. So the CIA assumption, so conditional dependence assumption, we usually will say CIA. This CIA basically say conditional on the observed characteristics X. The potential outcome, the value of potential outcome is unrelated to the treatment assignment. So this basically implies the X, for example, age, is a key factor that determines the treatment groups and control groups, their potential outcomes difference. Okay. So after you control the age, so make the treatment group and control group have the same age, their potential outcome on average will be the same. Because the X, you can consider X is determining your potential earning without the treatment or with the treatment, something like this. So on average, the treatment group and control group, if you compare, they are all the 40 years old, their earning will be the same. Potential earning will be the same. And also the potential earning, if they join the job training program, are all the same. Okay. So due to this assumption, basically you can eliminate selection bias. Because this is selection bias. What does selection bias come from? And the intuition is you basically assume the selection bias, the treatment group and control groups, their difference is only due to these observed characteristics. So after you make the treatment group and control group have the same characteristics, the same age, there are no difference between treatment group and control group. The only difference is the treatment status. Okay. So then you can claim you can get a causal effect. Okay. So in job training program example, the treatment is join job training program or not. And Y1, the potential earnings if join a job training program. And Y0 is the potential earning if you decide not to join job training program. Okay. And the X could be some observed characteristics like age or education, something like this. Okay. And this is just say similar things. The conditional independence assumption basically can claim if you compare the people with the same age, the same educations, whether they join job training or program or not, this decision is unrelated to their potential earnings. So if you fix their age, their potential earning will be similar because the age is the key factor to determine your potential earnings. So now you fix they are the same. So by this definition, on average, their potential earning will be the same. Okay. So that means after you control age, the treatment group and control group will be comparable. It's the apple-to-apple comparison. Okay. But this is one assumption you need. Another assumption is also you need is the common support assumption. So this assumption basically say, given some value of your characteristic, for example, the age 40, compare the people with the same, all have the their age are 40 years old within this group. Whether this is a probability of getting treatment should be below 1 and 0. So why we need this assumption is because it basically suggests you need, for each value of the covariance x, there is a positive probability of being treated and untreated. So you cannot have the sample, for example, you are age 40, you can only get a treatment and without only have the treatment group and no control group. So if that happens, you do not find any people from a control group who are age 40 that can help you to match the treatment group. Okay, so we cannot have such thing happen, this probability. Given they are 40 years old, these characteristics, the probability of getting treatment is 100%. So that means within the people who are age 40, no one did not get a treatment. No one did not get a treatment. So everyone get a treatment. So that means you do not find any people from a control group has these characteristics, age 40. So in that case, you cannot use match, as I just said before. You don't find any people who have the similar characteristic that can help you to match the treatment group. So we will make the treatment probability given the some characteristics value, they must be between the 0 and 1. Okay. So this will ensure there is a sufficient overlap in terms of the characteristics between the treatment group and the control group. Okay. Otherwise, we cannot create a match sample. Okay. So any question for this assumption? Okay. So based on these two assumptions, we can try to know what kind of causal effect we can get from matching method. So again, the only thing we can just compare is the observed difference in the average outcome between the treatment group and control group. But the matching method suggests us we need to control some key characteristics X. For example, age. We need to make the treatment group, those who decide to get a treatment and those who decide not to get a treatment, their age need to be similar, or education to be similar. Okay, so based on this, we can compare their outcome because we can eliminate selection bias by CIA assumption, conditional independence assumption. So that's very similar arrangement, just add this term, minus this term, add this term, and you will decompose two things. One is causal effect, another is selection bias. But due to the assumption, after you control these key observed characteristics, they are fixed, they are the same between treatment group and control group, their potential outcomes will be the same. So this term will be killed. This term will kill. So it will become 0. And then we can claim we get the causal effect of for the treatment group with the age 40, for example. So matching can directly help us to identify the conditional causal effect for the treatment group. Okay, that is, we can identify the causal effect for the treatment group with age 40 or high education or some characteristics, some subgroup. Okay, and then you can also further know also can identify the causal effect for control group, because due to the CIA assumption, after you control the observed characteristic, after you control the age, whether you get treatment or not is independent of the value of potential outcome. So this term will become the same as the condition for the control group. And since our sample are all from treatment group or control group, it also can help us get a causal effect for the conditional causal effect for whole population. But the causal effect we get is only for this specific subgroup, the people who are 40 years old. Okay, if treatment group and control group are all 40 years old, we can get a causal effect. Okay, so it sounds like it's very restricted, but we can also further using other things, other method to help us to get the average treatment effect on treatment group and average treatment effect on control group and also average treatment effect for whole population. That's the things we will get. I will let you know how to get this later. So any questions? Okay. So how to get this is very simple because now the matching method can help us to get each subpopulation their causal effect. For example, we just match people who are 40 years old, who in the treatment group and who are in the control group, their earnings difference to get this job training effect. And we also get the age 41, age 42, age 44. So we just take average over these X characteristics, and we can get the average treatment effect. Okay, so basically just take average to all these conditional average treatment effect to all subgroup, you can get the average treatment effect for whole population or for the treatment group. Okay, and why we can say less is due to this math formula. It's so-called law of iterated expectations. You should learn this in your statistics class. But here I just give you some review. And this actually say some very basic things. But people might find it's hard to know what does this mean. It's just say there are two ways to calculate the average of some variable. So one way is direct way. Another way is indirect way. This is you can calculate the average within the subgroup and take the average over this subgroup. And you can also get the average of the y. Okay. So intuitively, we have two ways to compute the average outcome. The first way is this expectation of y. What does this mean? Is the y variable times the probability of specific value that will show up. Okay, so you will get average. Another way is you first calculate the average y over some subgroup. For example, you calculate the average earning for the female and times the probability of female and male. And you can also get the average earning for whole Taiwanese people. So this just say two ways to calculate this. The first way is suppose we want to calculate the average earning in Taiwan. And we know 40% of people in Taiwan earn 1 million NT dollars, 40% 2 million NT dollars, 20% 3 million NT dollars. So how can you get the average? Just 1 times 40%, 2 times 40%, 3 times 20%, you get 1.8%, or 1.8 million NT dollars. And law of iterated expectation is say, you can use another way to calculate. You calculate the average earning for some subgroup, and then take the average. For example, you calculate the average earning for male is 2 million. And average earning for the female is 1.6 million. So that is this term. Male and female. Male and female. And take the times the share of male and female. And you can also get the average earning in Taiwan. Okay. So that's exactly the same thing we want to do. We first calculate the causal effect for some subgroup for male, or because we compare the treatment group and control group, they are all male, all female, and their difference. And based on the thing we just said before, it gives us causal effect. And then we just take average over the gender or over the age, and then we can get the average effect for whole population or for the treatment group. Okay. So any questions for this? Okay. So by doing this, I just say you can get a lot of causal effect because you now you only have the conditional causal effect based on the same age, the same education, specific value of education or specific value of age. And due to the law of iterated expectation, you just take average over the age, the causal effect for the same age, specific value of the age, take over of this whole subgroup, and you can get the causal effect for whole population, just due to this law. Okay. And similarly, you can get this is just an example, or you get the average effect for the male and average effect for the female of the job training program, and you just take the average of these two terms, you can get the average effect for whole population, because whole population either male or female. Okay, and you get the causal effect for male and female, then you should be able to get the causal effect for whole population. Okay, and similarly, you can just focus on the treatment group, this subgroup, and within the subgroup also have female and male. You just take average. And you can also get a causal effect for the treatment group. And very similar for the control group, causal effect for the control group. Okay, so that's very similar. Okay, so any questions? Okay, so now we know what kind of causal effect we can use matching to identify. And next thing is how to estimate using the data or using our sample. So again, we usually only have sample that is part of the population. For example, we just have 1,000 individuals, and 500 they join the job training program, and 500 not join the job training program. So one is a treatment group and control group. Right? And we want to know the effect of the job training program. So how can we do that practically? Is we want, for example, we want to estimate the causal effect on the treatment group. Okay. So in that case, matching estimator can be constructed like this. Okay. So we want to know how does the job training program affect the treatment groups, their earnings. So now we want to match the people who get job training program. So we want to match the treated units, these people. Okay. So the thing is, we only know the outcome, they go to the job training program. But we don't know what if they do not go to the job training program. So the matching method suggests we can impute the Y0 using the untreated units in the control group. And what kind of control group? What kind of untreated unit? Is the untreated units, they have very similar characteristics. For example, the treated unit, the observation J in the control group. This individual, they have very similar characteristics as the treatment group, individualized treatment groups, their characteristics. They have the same age, for example. And we find this from the control group and use that to match with the treatment group. And every treatment groups, the individuals, we do the same process. And some take over the difference, average difference between these two groups. So we can get the average treatment effect on the treatment group. Okay. So that's basically the same thing. I just used the example to demonstrate, and this is just the math to formally display what does I mean. Okay. Okay. So I think we can have the break, and we can restart.
就是这两个为什么相等？
因为那个 CIA 那个假设造成的。因为那个假设说，只要控制了 x 之后，就是我们比较都是同年龄的。
对。
那个会不会得到 treatment 这件事，就跟你的 potential outcome 没有关系。对，也就是说，实验组就是你有没有得到 treatment 跟有得到 treatment 跟没有得到 treatment， 他们的 potential outcome 就会一样，很像。
所以他的意思是说，如果在 CIA 的假设下，他们两个这个都是 50% 吗？
就是
拿掉这个最重要的这个，比如说 A，
对，
控制这个的话，你有没有得到它都是一样的，那这样不就代表说它这两个都是各一半，那就是50%。
什么意思？为什么你觉得是50%？
因为跟这个东西，就是跟你有没有，就是有没有得到受到那个实验，就是
对
啊，
对。
所以他如果我问的话是，如果我们把这个东西 control 住了的话，那你有没有得到？你是有没有受到那个实验的probability 会一样？
对。
哦。
对，所以他有没有得到这个 treatment 会一样，那的几率都一样啊，的几率都一样，然后而且是跟他的 potential outcome 没有关联。对，所以如果是没有关联的话，表示说，第一都是 treatment group 的这个 potential outcome 的值的差异，也会跟 control group 值的差异一样，因为他们的 y1 会一样。对不对？就是我刚刚前面讲的这个，主要是这一边他们会一样，这个你可以同意吗？就是只要比他这就是说这个假设就是说，只要比较同样都是同一年龄的实验组跟对照组，他们的潜在的薪资是没有差别的。平均来说没有差别。对，那这两个没有差，这两个是一样，那他们两个的差距 y1 减 y0 也会一样。
OK。
对。
OK。
这个减它也会一样，因为这两个 turn 都一样。
对，所以
相减也会一样。对。
对。
谢谢。对。邱老师，你有收到我的信？哦，没关系。哦，对，这样就不好。对劳动市场影响，比如说薪资，就是因为中国崛起嘛，这是 first stage 会不会就下降，然后就业失业，然后接着最近这几年开始去看，比如说对婚姻，甚至还有看生育的影响，然后当然还有一些跟政治有关，就比如说今年这一篇什么 AI，它应该算蛮有代表性的。 这个变异来去就不一样，不一样。他可能会看的是更细，像康体线或者是康体这种。中也有可能，只是他们因为他在美国只要可以弄到很细，他可以弄到很细。对对对对。进口，对，因为美国是一个比较靠内需的一个国家，所以他就是可以要么自己。类似讲的，类似，但实际上因为它还有用个 instrumental variable，对对对对，所以它里面就是一直在，
就是跟任何
对，但是概念上就是它没有它那个 local 的地方，中国的产品到底占多少？
它好像不是有问题吗？那他那时候也不知道。今天早上问到。
对对，应该就是我记得的第一篇，但是经济那边做，对对对对。但是我后来又看到有一个，我随便找的，就是另外一篇有在做 legislative response， 所以有可能有点接近，但是你可以看一下，我不确定那个是在做什么。没有没有，这一篇没有。有一篇政治的其他，它发在 comparative politics 什么东西 ，politics 啊，但是好像还不够起来。第二个，但这是我自己稍微 search 一下就看到这样，有看到这样。对对对对，但是我不太清楚他们是做像你这样讲的这个，对对，有可能不太一样。对，他就会说他是有道理。哦，这样也是可以，这样也可以，或者是，你的意思是让它 match 一个，把它变成3个对1个。我觉得没有，应该是在实物上，如果不 allow replacement， 这后面这2个就去找跟它接近的，就没有一模一样，就找27岁或26岁去配它，那它就会差一点点。它好像比较没有像你刚刚讲，你刚刚讲的方法，但是我听的不是这样，它不 allow replacement 就是这边不可以重复用，那就只能再用一次的证照接近，所以那就你可以在26，就是20，就是你20都会用，所以通常做 match 的时候，控制组会比较好，因为你比较多可以拿来去配，如果你控制很少，你很容易就可以导不出好的配线。如果你的 effect 是想得到这个区域对实验不会影响的话，变数比较多。哦，如果你控制有比较多 characteristic， 就很难找到很像，因为你要既是43岁又要大学，你就很难。所以这个要怎么处理，最后就会是后面叫 physical match。
Let's take a So you have 435 at least.
Yeah.
我会对打一组，现在我在打一组。你写这个不是水水，
应该太热了，
将会写到给太热。
会不会？会很闷吗？还是还好？有点冷。对，因为那个框打不开，不知道为什么，它打开掉下去。
You will get 435. 那个更好听。
我觉得开这个蛮好的，但会不会？
I asked you to snap.
空气啊。
没有没有，其实很好，所以演到
那 sorry。
这不能喝酒，那是问题。
还是整个门打开，但我不确定会不会外面很吵。但我觉得大概还好。
有点点。
How do you think it is?
We did the first. It's a little bit. I did monetary fiscal policy one. The one about the variables. 没有，那哇哦。
Sorry, but I can ask you.
不按很生气吗？
So this is like I had done. So you see like the first one.
幸好我没有休息这样，幸好我没有休息。
Yeah. I really want to do that.
我们3个休息量的人，哇！他们1个多小时。
把你们放进去。
然后讲出来的那个就从回到原点，然后把它想好，然后来源。
So I just remove the rows.
真的，我是觉得我是对这个有点我3选1选对。
奇怪。
我刚刚说总名是对的。
总结很轻松，而且他教的很清楚。
而且有影片。
对，可以躺着看。
对。躺着看什么概念？
Okay, so let's start today's the class. So here I just let you know how to estimate the average income treated using the matching. So it's very similar. You want to match the treatment group. So the treatment group you can only observe those who get a treatment, their outcome, and you don't know what if they do not get a treatment. So Y0 you need to impute. And using the control groups. And what kind of unit you need to choose is the observation J. Because observation J, his characteristics are very close to the individual I, the treatment groups. So you basically choose this guy based on their characteristic, whether they are similar to a treatment group treated unit or not, and use them. And each individual I in the treatment group, you find corresponding units in the control group with the similar value of some characteristics. You do this process for each individual in the treatment group and take an average of this difference, you can get average treatment effect untreated. Okay. But sometimes you might not you find a good match for maybe two units in the control group have very similar characteristics as a treated unit. You can just take average of these 2 units or 3 units. That's basically something we just mentioned in the previous example. But if you have more and more characteristics, the perfect match are not often available. You just find the closest one. Okay. And similarly, maybe you want to estimate the average treatment effect for the untreated, for the control group. And in this situation, you can observe the outcome if they do not get a treatment. So you can observe this. So the thing you need to impute is the potential outcome with the treatment. You don't know the control group, what if they do not join the job training program, what's their earning. So this matrix suggests you should try to find the observation J in the treated units, treatment group. They have very similar characteristics as the control groups, for example, in individual I, and use their outcome to replace Y1. And you do this for each individual in the control group and calculate their difference and take the average over this difference over a whole control group. You can get average treatment effect on the control group, for the control group. Okay. And how can you get estimate the average treatment effect for whole sample? It's also very similar, since the whole sample either get a treatment or not get a treatment. So for the observation, if they get a treatment, you need to impute Y0, because you don't observe what if they do not get a treatment, using the control group. And if this observation is untreated, is in the control group, you need to impute Y1 using the treatment group. Okay. So you do this either for one for the treatment group, one for the control group, and sum over whole sample. You get the causal effect for whole population, whole sample. Okay. So any question for this? Okay. Okay. So there are several, I think so far you should notice there are several problems might happen. For example, we are not just have one characteristic need to match. We have more than one characteristic. In the practice, we have maybe 10 variables need to find the closest value for the treatment group. So in that case, we might need to use some way try to measure what do you mean by closeness? What do you mean why this sample they have similar characteristics as the treated unit, a treatment group? So you need to define if we have more than one variable, one characteristic. For example, we have k characteristics. So we need to define some distance matrix to measure the closeness to construct the match sample. Okay. And the idea is also very similar. We need to calculate their difference. But now we might have 10 or more than one variable. Okay. So how can we do? We can use Euclidean distance. It's just very simple. Now we have k variable. So for each factor, for each characteristics, we try to compare their treatment group and control group, their difference. But now we have other variable also need to calculate, and we calculate for each sample. We calculate k variable, this difference. For example, we have age, education, these two variables. First, for this individual I, we try to find someone in the control group. They have very similar age, and we calculate the difference. And second, we calculate the education difference, and we take over sum over these two characteristics, their difference. Okay, and we can get this measure. And if this measure is very small, means is the smallest one, we will use this individual as the good control group to match the treated unit. Okay.
Professor, can we see that with the first example for this? Like, I don't know, like an example of how to.
This one?
Yeah, like how can we find the treated distance, like with the initial example that you gave us in the first period?
First example.
Yeah.
Oh, so in this, it's just first. So in the very beginning example, just age, one variable. So it's just k. Let me. Let me. Maybe I should say. So in the beginning example, k is equal to 1, right? So it's very also similar, but it's just 1. So xi k minus kj squared. So here, for each individual I in the treatment group, you just find one person in a control group that have very similar age. Okay, but now k could be 2. You need to also find another dimension in education. So that means for each individual I in the treatment group, you need to calculate the difference in terms of age and also education, and sum them together, sum up, and take a square. And you can calculate one value for individual J, for example, the unit 1 in the control group. For example, this number could be 5. And unit 2 is 10. And unit 20 is 1, for example, this value. And you might pick the lowest one to match the individual 1 in the treatment group. Okay. So in the very beginning example, here is more simple, it's just one dimension. So you just calculate the age difference and use the lowest difference as the match sample. But here it's more than 2. So you need to use this way, try to sum up all the difference in all characteristics. So for each individual I in the treatment group, you need to calculate, for each individual J in the control group, you will calculate one number.
So the X would be the outcome.
No, X is the characteristics.
Or the age, so if it's 10.
So if disease is 1, just age, this just age, right? And you find the individual J in control group, you try to find the difference age between the individual you want to match. Try to find the smallest difference. And this guy will be matched with your treatment group.
If they're both 28, like in the first example, then it's just 0?
Yes.
Oh.
Yes. Just 0. But sometimes it's not 0. That's the example I create for the teaching. Yeah. 0 means, 0 should be the lowest one. Yeah. But usually, maybe you go through whole process, calculate every individual in the control group. The lowest one is not 0. You just pick the lowest one. Yeah. And you can imagine if the variable is 2 or 3, this number will not converge to 0. It's hard. Okay. So any questions? Okay. Okay. But there's a drawback for this measure. Because this measure is not invariant to the unit of the x, the scale of x. Because, for example, maybe there's the different, the unit you want to measure the weight. You use gram or kilogram. So 1 kilogram is equal to 1,000 gram. So if you use gram to measure your weight, this number will be very big. But if you use kilogram, they will be very small. But actually they maybe are the same. Okay. So you need to take this into account by trying to adjust. So how can you adjust? Basically the method is very simple. You just divide by the variance. Okay. So this is just matrix. So but I can I do not use matrix. You can just say the formula will like this. Oh, you calculate each characteristic difference between treatment group and control group, but you need to divide by the characteristics its variance. This is the k characteristics its variance. For example, age variance over the sample. And since your denominator and numerator both use the same units, they will cancel out. So it will cancel out the effect from if you use different units. Okay, so this will invariant to the unit you use. That's so-called a normalized Euclidean distance. So usually we use this to calculate the distance between the treatment group and control group. Okay. But actually, this is not in practice we will do, because you can consider the matching become infeasible if you have too many covariates. Okay. And this is also true if we divide our covariates into more rough categories. Okay. For example, we have k covariates. K characteristics need to match between treatment group and control group. For example, we just have age and income. We just need to match these two variables. And we just categorize age into young, middle age, and old. So actually originally is 1, 2, 3, 4, 5 until 80 or 90. But we just roughly say young, middle age, and old. And income is also continuous variable. So if you want direct match income, you might think it's impossible. Or we just say low income, medium income, and high income. So in that case, just two variables, and we roughly make each variable have 3 categories. Now we need to match. We have around 6 groups. We need to match 9 group we need to match, like young individual with low income, young individual with medium income, young individual with high income, to match this. So if this individual in the treatment group is young individual with low income, you need to find someone also have within this category. So this the number of classification is 3 power k. So if you have 10 variable, how many category you have? It's not 9, it's 3 power 10. It's 60,000. So you need to match this. There are 60,000 groups. You need to try to find someone within that group in the control group. With that in that category in the control groups. And sometimes it's maybe you cannot find it. Maybe young people with low income only exist in the treatment group. And you cannot find anyone who are young and low income or their father's education is at university, mother's education is elementary, which exists in the treatment group, but never exists in the control group. So in that case, basically, you violate the common support assumption. You cannot find a good match. So in that case, you cannot do that. Okay. So that's why we need to learn more practical way to implement matching is so-called propensity score matching. That's very popular in the social science or life science. They use this method to when they implement matching method. Okay. So any questions? Okay. So the main idea of propensity score matching is instead of matching over k dimension, very high dimension, 10 variables, you have a lot of categories. The method of propensity score matching allow matching problem reduce just single dimension. You just need to match one variable called propensity score. So what is propensity score? Propensity score is defined as the treatment probability conditional on a lot of observed variables, x. So basically, this is the probability based on a lot of characteristics. Use that to predict who can get a treatment or not. Okay. So this is the average probability given these characteristics. So you use in practice is you use age, education, your father's education, mother's education, family background to predict whether this guy get a treatment or not. It's probability. So you will generate a probability of getting a treatment, and this probability is called propensity score. And the thing you need to match is just match this probability, this score. And later we will have the theorem to show that if you match propensity score is the same as match the k observations, k variables. So then you will reduce the matching problem from very high dimensional impossible matching to the just single dimension. You just need to match this score, the treatment probability. And the intuition is you can consider this propensity score actually is based on the 10 characteristics. These characteristics, its effect. It's kind of like summarize the effect from the characteristics from these k variables. So this is kind of summarized measure for these k variables. So that's why this can work. Okay. So any questions? Okay. Okay, so these two statisticians, in 1983, they proved under the CIA assumption, the conditional independence assumption, basically is implied this term. So that is conditional on propensity score. So you compare the treatment group and control group, treated unit and untreated unit with the same propensity score. For example, 0.1. They are all 0.1 propensity score. The treatment probability is 0.1, 10%. If that, you compare the unit with the same propensity score, whether they get treatment or not is independent of their value of potential outcomes. Okay. So the difference between CIA and this is instead of control X, you just control propensity score itself. Because propensity score actually is the X characteristics, its function. So it's kind of summarize its impact effect. Okay. So that can help us to reduce high dimension problem to the single dimension. We just need to match this. If this is true, CIA implied this. So that's so-called propensity theorem. Oh, so what does this mean? This means suppose CIA holds. So what is CIA? CIA is a conditional on we compare the treaty union on treaty union with the same age, the same education, the same everything, observed thing. Whether they get treatment or not is unrelated to their potential earning, potential outcome, the value of potential outcome. And this theory say this condition, this assumption imply this. That is, we just compare the individual, the treated unit and control unit, untreated unit with the same treatment probability, the same propensity score, like 0.1. If they all have the same propensity score, whether they get treatment or not is random, is unrelated to any characteristic, any the value of potential outcomes. Okay. So then we can just everything we just do in the previous class, we can just match propensity score, and then we can get a causal effect. We don't need to match 10 variables, okay, which is impossible. Okay. So why this proof? Why this is true? So the goal of the proof is this condition given, and we want to show this hold. This is hold. And why we want to get this? Why this is implied this is because this basically suggests, given the propensity score, you don't need to conditional on your potential outcomes, because propensity score basically is like the X is the key determining for your value of potential outcomes. So after you control it, basically you don't need to condition on this. So we want to show this term, the probability of getting treatment for this condition on the value of potential outcome and propensity score is equal to the treatment probability given the propensity score itself. Okay. So we want to show this is the same. And if this is the same, this means you just need to control the propensity score. That will make the treatment status is unrelated to the value of potential outcome. Okay. So first things is, given this is true, and we want to show this term, the probability of getting treatment conditional on this is equal to this. So why this is true is, this is the expectation of whether you get treatment or not. So this is why this is true is,那我知道有这边。So expectation. So first equal is because expectation di conditional on your potential outcome propensity score. This is actually based on expectation this is equal to 1 or 0, right? So 1 times probability of treatment conditional on yi, y1, yi, y0, and p. Plus 0 times this probability. So it's the same. So this term is 0, so it's cancelled out. So that's why this is equal to this. That's why we can say this is equal to this. Okay. It's just very simple. This is the definition of the expectation. Okay. And So this term is okay, and this term is law of iterated expectation, which you just learned before. You add this term, you take over the subgroup over the x. That will be the same thing as this term. And the next term is due to the, when you control the covariates, the x characteristics, it's the same. You don't need to really control the propensity score because propensity score is a function of the x. It's a set of the x. So you don't need to control this. And finally, this one, y is equal to this one, is due to the CIA assumption. Because conditional on x, basically, the value of potential outcome is already controlled. It's already fixed. So this one. And this one equal to propensity score is again due to the expectation definition. That will become P of x. And then you can prove this is equal to P of x because given the P of x, this directly gives you these terms. Okay, so similar argument, you also can prove the probability of getting treatment just conditional on propensity score is also the same as the propensity score. So these two terms will be equal. That means conditional on propensity score is the probability of getting treatment conditional on propensity score is the same as the probability of getting treatment conditional on value of the potential outcome propensity score. They are the same. So this basically suggests this. Okay. So intuition is the propensity score is the function of the x. Basically, this propensity score, just one single number, can summarize the information within these k variables. Okay. So that's why you don't need to directly control the x. You just control this single number. Okay. And why this works is due to this theorem. Okay. But intuition is you can consider this kind of like summary measure for the x, the k variables, the information of all the k variables. Okay. So any questions? Okay. So the propensity score theorem is very beautiful. It says something, say the only covariates you really need to control for when you do the matching is probability of treatment itself. Is this. You don't need to control so many variables. You just control this variable, propensity score. Okay. So that will make the problem very similar. Instead of control x, now you just control propensity score. And you will get the causal effect, conditional causal effect for the treatment group with the same propensity score, with specific value of propensity score. For example, the value of propensity score could be 0.1, 0.2, 0.3. And we can get a causal effect for these people. The individual with propensity score, his propensity score are 0.1. Okay. And again, we get this, and we using law of iterated expectation, we can recover the average effect, causal effect for whole population. So that's very similar. So everything are similar as I just mentioned before. Just replace the x to the propensity score. Okay. So I will not spend time to go through again. Okay. So any questions? So practically, how we use the propensity score matching estimation. There are two ways to estimate causal effect of treatment using PSN, propensity score matching. One is so-called the nearest neighbor. Basically, is by his name, is by matching each treated observation to untreated observation if they have the same or similar value of the propensity score. So if they are all 0.1, we match. 0.2, we match. Or use some reweighting approach, but we will not discuss this approach. We just focus on this nearest neighbor approach. The weighting approach is we don't need to match each individual. We use some reweight based on the propensity score you estimate. You use this as a weight to calculate the causal effect. But we will not discuss this. So how can we do that in practice? The first step is, there are two steps using estimate causal effect of treatment using propensity score matching. The first step is you estimate the propensity score. Okay, so what is propensity score? Is you use the k variables, try to predict, use these k variables, try to predict specific individual, the probability of getting a treatment, the probability of getting treatment for specific individual I. So basically, you run this regression using a logic or probability regression. So you, whether you get treatment or not, 1 is get treatment, 0 means you do not get a treatment. So that's you can observe in the data. And you have several characteristics like age, education, income, and use these k variable, run this logic or probability regression, and try to get the prediction. And this prediction could be d hat. This could be 0.1 for individual 1, 0.2 for individual 3, or extra. So every sample, every individuals, you can use their characteristics to get a prediction of the propensity score. And then you do matching. So you match each treated observation to the observation in the control group. They have the same or similar value of propensity score that you just estimate. Okay. So any questions? Okay. So what you exact to do is you run the regression and try to get the prediction of propensity score. So for example, unit 1, the propensity score is 0.28. Unit 2 is 0.34. And control group also, you can get based on their characteristics, age, education, a lot of things. And you want to find someone who are similar to the unit 1 in the treatment group. So you just need to find those who have the same propensity score. For example, unit A in control group. This is a good candidate to match individual 1. And this number you can consider is summarize whether these two individuals are close or not in terms of these k variables. Okay, because this number is predicted by or estimated by these k variables. So if they are similar, that means these k variables should be very similar between these two individuals. So you can construct, so every individual in the treatment group, you can construct the match sample that with the same propensity score. And then you will do the same thing, calculate the average of earning between the match sample and treatment group. And you can get a causal effect. Okay. So instead of match the x itself, you can just match p of x, the propensity score. Okay. That makes question much easier. Okay. So any questions? Okay. So we can get the estimate of causal effect. Every treatment effect untreated using the matching, using the propensity score matching. And final things I may not discuss a lot is how to do the hypothesis testing. That means you need to calculate the standard error of your matching estimates to know whether your estimate is significantly different from 0 or not. And actually, this is very hard math questions. And this has been known until very recently, until 2019. Imbens is Nobel winner last year, and Abadi actually is from political science or public policy. So these two scientists, they actually developed the formula to develop the asymptotic distribution and calculate the standard error of the matching, the propensity matching. Okay, so after their contribution, we can know whether this propensity matching estimate is significantly from 0 or not. Okay, otherwise we don't really know. Okay, so the contribution is they before that they have the problem is the propensity actually is estimate. Okay, and they consider this. They take this real question into account. Consider this is estimate, so they have something you need to fix when you calculate standard error. And after consider this, they basically get the right standard error calculations. Okay, so previous is not right. Okay, and basically, okay. So just brief. If you are interested, you can read their papers. Okay. So any questions? Okay. So here, finally, I would like to let you know how to implement the propensity matching using the data. So you can download the do file from the link. Class data do file matching. So you can replicate what I will discuss later by yourself. And also you need to download the data that I use for this example. This data. Okay. And I described in my slides. So the author want to examine these very classical problems in labor economics, try to examine the effect of joining the job training program on workers' earnings. And the paper is here. You can also read if you are interested. So we will use this as an example to go through the procedure implementing the propensity matching. Okay. Okay, so do file is here, data is here, and you need to install the package ps-match2. Okay, so we will introduce two commands, two packages. One is ps-match2, another is this. You will learn treatment of a key effect ps-match. That's two command, but this is default in the default package in this data, so you don't need to install. Okay, so I will let you know how to install the new package when you're using this data. How to install this, I will let you know. So the first step when you do propensity matching is you will try to test the difference in the outcome in the pre-match data. You want to show to your reader before matching actually is quite, you will get very different result if you before matching and after matching. That's why you need to use matching to correct the result. Okay. So first you test the difference in outcome and also in the covariates before matching. Okay. So just the raw data. So here the outcome is this RE78. This is the 1978 these people's earnings. Okay. After they join the job training program. So they want to evaluate whether the effect of the job training program on earning. So this is the earning you can consider. So if you can use t-test. That's something we do not discuss last time. So t-test, this is compared two groups, these variables difference. Okay, that's basically last time we want to mention, but we don't have time. Okay, and so this is put the variable you want to test, and this is put the group variable. So this is equal to 1 means treatment group, 0 means control group. So basically you want to compare, use t-statistic to evaluate whether the earning between the treatment group and control group, whether they are different or not. Okay, so you can use t-test this variable by treatment group or control group. Okay. So you can open the do file, the matching, and the first thing is test the maybe I open the data set. Open the data set. So the data set looks like this. This is the treatment group dummy. 1 means treatment group, 0 means control group. And they have several characteristics: age, education, race, marital status, and their earnings. 1974 earnings, 1975 earning, or 1978 earning, something like this. I think they don't have data for this, or I don't know why this is 0, but maybe it's they don't get job these 2 years. But the outcome here is the 1978 earnings. Okay. So the first thing is you use t-test to compare treatment group and control groups, their earnings, their outcomes, before matching, before we do matching. So you can do that. And that's the result. The result I just show here. That's the result. So the result is control groups on average their earning is 6,900, and treatment group is 6,300. So their difference is around 600. Okay. So treatment group tend to earn less than control group. So it's kind of like job training program is reduce your earnings. But whether it's true or not, we don't know. But the difference is not significant. The t-value is just 0.9. It's not very big. Okay. So the p-value very high means we should not reject the null hypothesis. Okay. Okay, and also you also try to test the difference in the covariance. Okay? Because treatment group and control group, their characteristics are different. That's why you need to use matching. If they are already similar in terms of all characteristics, that means they are very comparable. Means you don't need to use any method. Maybe the data is from randomized control trial. Okay. But actually, they are very different. If you use t-test, you will find their age. Treatment group tend to be younger. 2 years old difference. And this difference is significant. T-statistic is 2. And p-value is 0.005. So it's below 1%. So it's significantly different from 0. No difference. Okay. Okay, so then you do propensity matching. So after you check everything in the pre-treatment period, data, you might because you find their characteristics are quite different. So that's why you need to do matching. So you can use this package t-effect ps match. So t-effect is a package, a command that can do a lot of matching. So they have a lot of options. And here is one of the options called PS match. This is allow you to do propensity matching. But you can also, if you are interested in this, you can help T effect. They will let you know other method, but I just focus on propensity matching. Okay. You can explore by yourself using the help. And the information you need to put in this command is outcome. Oh, here is the earnings. And the treatment is whether you go to job training program or not. And other covariates, age, education, other things. And there are several things you can choose. For example, you need to also let data know how you estimate your propensity score using logic or probit. That's something you can change. Use logic or probit to predict the propensity score. And also, you also need let data know what kind of causal effect you want to generate. ATE is average treatment effect. You want to know causal effect for whole sample. But maybe you want to know ATET is the average treatment effect only for the treatment group. It could be different. And this NN is the number of match per observation. Okay, so that means how many observations from the control group or from control group you want to match with your treatment group. So for each, so default is 1. That means each observation in the treatment group, you just pick one unit in the control group to match them. But you can say 2 or 3. They will just pick 3 to take the average to match the treatment group. Okay. Okay. So any questions for this? Okay. So I finished this example and then we have a break. So our outcome is earning treated is our treatment variable and the covariates and we want to know the average treatment effect untreated. Okay. And this is average treatment effect for whole sample. And this is the result if you implement. The result will give you, for example, you focus on the ATE. This will give you ATE. And basically, they do the same process I just mentioned in the previous slide. They calculate the propensity score first and choose and match the individual in the treatment group and control group with the same or similar propensity score. And if you want to know the effect for whole sample, it will give you ATE. And the result is if everyone in the whole sample get a job training program, their earning will reduce 300. But it's not significant. So the standard error is AI robust. It's a body imbalance. So that's why they call AI. It's the paper. The paper I just say. Until 2016, we know how to calculate this standard error. So that's why we can conclude some calculate p-value and this called t statistics. And based on this, we can know it's not significant, different from 0. Okay. But their ATT, the average treatment effect on treatment group is different. They find if the job training program actually can raise the earning for those who join the job training program. Okay. So for whole population, no effect. But for the treatment group, have some impact. So that's quite useful. I mean, because maybe policymaker only focus on those who decide to join the job training program, their effects. And based on these effects is significantly different from the 0. Okay. That means might increase their earnings after taking a job training program for the treatment group. Okay. So maybe we can have the break and then we will finish this. Okay. 一个是他的意思就是，对对对。我觉得 every tree 和 on tree 应该没有用，因为你就是 target 那些会需要 job training，所以你会想知道 job training 对这些人到底有没有用，你倒不会很关心 job training 对一些没有参加的人，所以也表示说应该也不是很关心对全体，因为全体就会含那些本来就不会参加的。就是，但是这个到底有没有用，可能就看情境啊。对。
Yeah, I was not.
Ah, no sé.
没参加。对。所以其实表示 ATU 就是没有参加的那些人的 effect。对。这个其实某种有点隐含，可能那个 selection bias 没有完全解释。对，所以 observe 的这个方法还是没有解决完全的东西，因为往往 observe。
我想问一下，那个 scope 那个它的概念跟那个组成分子像，就是把那个它的
哦，对，有一点概念，就是 idea 像，可是做法上就是也不太一样。对。但概念都是降维啊，
然后去抓它的特征。
对，就是把它summary， 对，截取出来。对。
就是在问你，因为就是我比较想要学就是这方面的东西，那你觉得就是我需不需要从那个什么 data structure 里面学，还是说只要去学它应用课程的方面比较好？比如说那个什么machine learning 或者是其他的数据分析的课，就是应用方面。
对啊，我觉得除非你想要了解背后理论，不然你可以直接学应用，就是你真的只是要拿资料，然后用那个，所以你大概要了解是直觉啊，然后数学那个推论不是需要真的很了解，直觉，然后怎么操作写 code 跟软体，
反而是做方面。
对啊，这个看你的目的。如果你是想开发新的方法的话，当然你要第一个了解所有的东西。但是如果你只是想用现存的方法，你比较需要了解实际的。
对啊，因为它就
实际使用。
没有说到需要去上那些很基础的课这样。
决定说
就看你的目的。对，如果你的目的只是应用，是真的不需要，因为人的时间也有限。对，但是你可能要了解它的概念，就是为什么这个东西可以用，或者它的目的是做什么。贝塔就是估计啊 ，log 你考一个 logic，
我看你手机。
对，然后你考一个回归就会产生贝塔，贝塔就是那个。然后就是用这些系数估计出来的系数，加上这个资料实际的年龄、实际的教育程度，丢进去这个式子，就会产生一个预测的 event score。不是，这个是你跑一个 logic problem 的回归式，它会产生出来。
办
这个就是回归系数。
送我，
对，
无法接受没有注音。
对。然后你再把实际资料每一个样本点都有 x1、x2、x3这些数字，搭配这些系数乘起来加起来，它就会 generate 一个地图的预测这个人会得到 treatment 的几率。这个会是一个这个在跑违规的时候它是1或0，可是你 predict 之后它会变成是一个0到1之间的变数。
我当初花了3天，
那个就是 propensity
去熟悉它。
对，介于这之间，因为这个就是他有没有拿到 treatment 的一个几率。但是它实际在 data 上是0跟1，可是你这边是要产生另外一个新的变数叫 propensity， 这个是用这些它的特性去预测它会不会得到 treatment 的几率而已，所以可能是0.5或0.6。对。那他们说这个 theorem 就是在说，只要 match 这个数字就好，就是你在实验组那边有一个人，他 propensity 是0.5，那你就要去 control group 那边找一个 propensity 估出来也是0.5的这个 score， 配这些东西，相当于配这 x 10个变数的 x。
那它的名字叫什么？
对，有，但我还没有时间完全了解。对，我们可以之后，反正我看我会再跟你说一下。
北女啊，北女字是黄色，台湾名是白色啊，我那个很明显不一样。
对，这个
老师到门口那个电梯那边超看傻。
对，怎么排？你可以先写一些，然后再来排。对，但你以为先讨论？
没有。
哦。
干嘛啦？闹奇怪啊！对啊，
其实我不太建议讲，但你听起来知道
他们群都在哪里？
男女的薪资的差异、劳动条件差异、一个很细的差异，还有产业差异。对，
我本来很久了那个。
但我觉得这可能有一些蛮主观的，你可以不用讲那么多。你其实应该有几个重点，但基本上我觉得可以在文章里面你就回顾那些内容就有关系的内容就好。你的文章目前看起来，第一个会看的就是台湾劳动市场里面 work from home 的
我看也在去。
然后最后会去看说不同 work from home 能力的样本，它受到疫情的影响，是不是 work from home 能力比较高的比较影响比较小？所以你大概是在讲这个，所以你的文章其实最重要第一个就是会说到 work from home 这件事，然后你可以讲就是我可以去放一些work from home 的以前跟以前这个东西，但还有然后可以讲一下。其他国家可能开始有这些讨论，或者是 measure， 但它算出来的比例或怎么样？
如果碰到一些时间点是那个类似，
因为这个可以跟你后面第一部分你可以讲一些国外情况，然后你这边讲，
我是希望你教，
所以你可以第一个国外情况就
然后可以按下载就
那第二部分其实有可能第二部分是回到课
es que ella tiene una teoría necesitamos el trabajo 这有些苦慢
其中就是你要跟那个后面要想不用讲一些我开始。
Oh, English is really fast. I pay attention and sometimes people may know. Sorry.
Okay.
Thank you so much.
Okay, so let's restart the class. Okay, so step 3 is do Venn matching estimation. So the following slides, I would like to let you know, understand how they do it, the matching process. Okay, so let's basically go very detailed about how this package works, what they calculate this average effect or average treatment effect untreated. So when you run this command, they give you one option is this, generate. And it can generate the match number. That is specify the observation numbers of the nearest neighborhoods that store. It will generate new variable called this. Basically, it will tell you, for example, unit 1, which unit match this unit. Okay. And give the generate this variable called match number. But this variable name, you can name whatever you want. But this variable will store the index, the observation numbers for the match sample, Okay. Okay. So this option can let you perform some post estimation based on the matching results, and that can help you more. Help you to understand the matching process. And there are several commands you can also use. Predict. After you run this command, implement this command, you can use this following command. Predict the propensity PS. So basically predict PS. PS means propensity. So you will generate a new variable PS1. That is propensity. So this PS is option. Okay. So what does this mean? So I implement this. So that's the same thing I just mentioned. And after you implement this code, you can do some, for example, you want to know the potential score for each sample. Because when you implement this, basically the data will not generate any variable that you know what's their potential score. Okay, but maybe you want to know, so that's you can implement that command. Okay. And also, this is the thing I just mentioned. It's let you know what is the match number. This means the first unit, which is the treatment group, the first unit. After you implement propensity score, the match in the unit is number 254. what is this? Is this guy. This number 254. This is a control group. These people, this individual. This guy match this guy. Okay. So I will let you know the process of matching. Okay. And you can also predict a potential outcome, y1 and y0. So for example, if you are in the treatment group, you get a treatment. The y1 basically is your outcome, your observed outcome, your earning, RE78. But y0 is the outcome, the observed outcome from the match sample. Okay. And then you can get the TE. TE is the treatment effect. That is the difference between this and y0. So I just let you know.
Professor, I was supposed to install a package to be able to do the predict.
Sorry?
Are we supposed to install anything? Because it keeps saying how post estimation can only be performed when the generate stub option is used during estimation.
Oh, you cannot generate. You mean you cannot use this?
That all worked out, but then using the predict, it's saying post estimation can only, it's giving error.
Really? Okay, let me check. Hey, but I can generate. But maybe I can check after the class. That's fine. So after you implement this, you can implement this predict propensity score. So this is option that generate new variable PS1 is propensity score. So now your data set will have propensity score. And this score is between 0 to 1. Is the number between 0 to 1 because it's generated by logic regression based on the characteristics you just put in. Okay. So each individual, each sample will have propensity score. Okay. And then you can implement this. It will generate potential outcome without treatment, potential outcome with treatment, based on the matching, propensity score matching. So it will generate y0, y1.
So is it just creating, adding this column to the raw data?
Yeah. Add, yeah. And I will let you know what they're doing. It makes sense actually. And then predict. TE is the treatment effect. That is the difference between y1 and y0. Okay. So you will generate this variable. Okay. And let me let you know what does this mean. ID. Sorry, let me do it again. Okay, so here is the result. So let me use this, the first unit as example. The first unit is treatment group. His observed outcome is 9,900 US dollars. So that's why his Y1 is the same as his observed outcome because he is a treatment group. So Y1 here is directly use his observed outcome. But the things we don't know is what if he did not join the job training program? What's their earning? That's Y0. So why they impute the y0 using this number is based on the propensity, because his propensity is 0.36. That means the estimate probability based on this characteristic is 36.66, 36%. You can say something like this. And within the control group, who also have this number is the observation 254. So let's see who is observation 2054. Let me clean the data. I just keep the first unit 1 and unit 254. You can see more clear. So, because they have the same propensity, so actually they match each other. So, the treatment group, the unit 1 is y0 actually is from the match control group, their observed outcome. So this 40,000 something US dollar is from this match sample. And then compare y1 and y0 using this propensity matching, because they have, you can get a treatment effect for this individual. So similarly, for the control group, they also have similar things. The observed outcome, they know y0, because the y0 is their control group. So their y0 is their observed outcome. So they don't know y1. We don't know y1 for this observation. And we also use propensity, try to find the same propensity, and this is unit 1, and impute them, and we can get a treatment effect. Okay. So the average treatment effect is take over all the individual treatment effect for whole sample. And average treatment effect untreated is just take all average for treatment group, for those who get a treatment. And average treatment effect on control group is just focused on the control group. That's the thing. So you can manually calculate this by yourself. Okay. But you can just implement this. It will directly give you the result. Okay. Okay. So this is one command you can implement propensity matching. So another command is called PS match too. So they have some difference, and one have some advantage, another have some advantage. I will discuss this later. So PS match 2, how can you implement? You put the treatment variable in the beginning, and then covariates, the characteristic you want to use for predict the propensity score, and put the outcome here within this outcome here. And this is also the number of match per observation you want to put. Usually it's 1. And logits you can also replace with the profit. And ATE is you want to calculate average treatment effect for whole sample. So it's very similar. And you can implement like this. Okay, the results are very similar. So there are several differences. But I would say the T effect PS match has one important advantage over the PS match 2. Is because PS match they can calculate standard error correctly, because their formula or asymptotic distribution is derived based on the Imbens and Abadis, their papers. So they calculate standard error right, and that's very important because that gives you the right statistical inference. You can conclude correctly, calculate a correct T statistic and p-value. Okay, so that's one advantage. This is very important advantage of this. But PS match 2 can allow you do the matching without replacement. So T effect only can do the matching with replacement. So that means T effect will repeat use several individuals that has used before. Okay, but PS match 2, you can have options say I don't want replacement. Okay, so they have several difference. Okay, but I would say this is more important. Calculate scenario correctly is important.
The replacement is like the very first example where 8 was used as multiple.
Yeah.
So it's like not going to be used more than one time.
Yeah, they have this option, and they can also with replacement, so they can do both. But this command cannot. This command cannot. Can only do with replacement.
It means it will be used multiple times.
Yes, yes. But they can calculate this correctly. Yeah. So, so if you don't want replacement, that means you don't want to use observation repeatedly, you can just say, put this option, no replace. They will do the same thing. Okay. So, after you implement the propensity matching, the final step is you can do some post-matching analysis. Basically, that's you want to show to your readers all characteristics now look similarly between treatment group and control group in terms of their distribution or the mean or the some variation. So you can use this command try to demonstrate the thing like the box. So you want to show their pre-treatment earnings are very similar. This gives you a box plot. This is before matching, they call row. And you can see control group and treatment group. Treatment group, their earnings are much lower than control group. But after you use propensity matching, they look similar. At least their average are similar, but not exactly the same. But it's impossible because you just match one number. But it can also match the K characteristics quite well. Not bad. And if you display the education distribution, you can, if you want to put distribution, you can, the option is density. You want to put education, and it will look like this. Before matching, treatment group tend to have lower education, you can see, lower education. But after match, looks not bad, similar. The only thing will be perfect match is propensity score. So before matching, the propensity score for treatment group and control group are very different. But after matching, they are almost exactly the same. Okay, and PS match too, command can also do similar things. I just let you explore by yourself. Okay, do very similar things. Box and density. Okay. Finally, I would like to let you know the main drawback of propensity score matching or matching in general. Basically, this method is very popular in the social science or in other nature science. Or especially for the medical science, or public health, they like to use this propensity score matching. And you can also find it's very easy to use because you don't need to find any exogenous change in a policy or randomly assign a treatment. You just compare those who get a treatment, those who do not get a treatment, and make they are similar in terms of all characteristics you can control. But the main drawback is actually this assumption is not very convincing because the variable research can observe or can control. There are some other confounding factor is unobserved for the researcher. And they might affect your treatment status and the outcome and generate a selection bias. So I would say this conditional independence assumption is not, you cannot verify basically. And also it's not very convincing. But you still can use that, but you just need to know there's some limitation and assumption made by this method. Okay. But after made this assumption, you can claim you get a causal effect. You just need to know what kind of assumption you made. Okay. Okay, so if you want to know more about matching, you can read chapter 2, match theory matrix, chapter 3, most harmless, and chapter 5, causal inference, mixed cap. So you can pick up one book to read. Yeah. Okay. Any
If you have to pick one of the books, which one would you pick?
I
guess
like this book. But this is written by Nobel Prize winner. But this is also good actually. Good. But this give you some intuition. Give you the code how to implement. They will discuss this. It's free online. It's free online.
The third one more easy to understand and apply.
Third. Yeah. Apply. They give you some code. Yeah. Okay. So finally, I would like to go through the data, how to use this data. So last time you know how to read the data, right? And then after you loading your data, you need to investigate your data. You want to know whether your data is correct or what kind of variable stored in this data set. You can use some command to implement. So you can see these two files, C3 exam data. So you can also again download from the link to get it. And also the data set you might need to download, like this one, CPS, you can download. Okay. So open your data, okay. And first things, you can type browse and edit. They will directly, basically, will show the data set, the browse. Okay, let me clean this. And if you type browse, basically it will give you open the data editor. So it's not very useful command. Okay.
Can you slow down, please? Because we were 5 seconds.
Okay.
For me, so.
Yeah.
Can you go back to where we download that data?
Okay. The browse, you just type this browse. It will open the data editor. So basically you implement this, it will come up the data editor. So it's, I just let you know, you can just do this to open. But you can also directly open by click here. Yeah. That's do similar things. And edit is the same. Edit is you can modify the number in the data set. Yeah. Okay. So the first command is describe. It basically will generate some summary of your data set. So you can just type describe this command and say you want to explore this data set. And it will generate a summary of data set of your data. So the output looks like this. If you type this describe using what the data you want. Okay? And it will let you know the number of observation, the number of variables, and the variable name, and the variable label. What does this variable mean? So give you some rough idea about the data. Okay, so that's the describe command. Another command can help you to explore your data is list. It shows up entire data within the result window. So basically, if you implement list, basically you put the variable you want to explore. This is the variable in your data set. So if you implement this, the result will show up in the result window here. So here you can implement. They will show, but usually your data is very big, so the result window cannot accommodate all the data show here. So usually, this command is useful if you restrict. You just want to see the observation 55 to 60. If you do that in 55, this means 2, 60. So that will just show the observation number from 55 to 60. So they will just show this data in terms of the variable you want to explore. Like here is 4 variable. So if you implement this, it will look like this. So you can know this observation there, household number, year, sex, and age. Okay? So that's this one thing. Okay, this is. And sometimes maybe you just want to know those who are age 37. So you can use if condition. So remember, if you want to make the condition the equal, you need to put 2 these things. Okay. So that will list this variable for those who are 37. Okay. So that's very similar. So I will not discuss. Okay. Okay. So another command called assert. Oh, because this is very useful if you have large data set. It's often impossible to check every observation using the list I just mentioned. But you might want to know whether your data set are satisfied with this condition or not. You can use assert. For example, sex, this variable, basically just 1 and 2. 1 is male, 2 is female. Typically, will not have more than 3, the number. So, but you want to check whether your data is right or not. So you can use assert. If this condition is right, they will say nothing. But if this condition is false, it will say false. So that means the sex cannot be bigger than 3 because in the data set usually 1 is male, 2 is female, no another, no 3. And age in this data set actually is below 85. So this will be false. So if you implement this, it will look like this. Assert say nothing because this is either 1 or 2. So this statement is true. But you can use this to check whether you have some abnormal data set, abnormal observation. For example, here, say this observation is false. That means no one have the sex is equal to 3 or bigger than 3. Okay. So this can help you to check the data. So it depends on your applications. Okay. Okay. So another command called code book. The code book can give you some extra information on the variables. So also very easy. You type code book and type the variable you want to explore. If you want to explore all the variables in your data set, you don't need to type anything. It will show up all the variables. So what's the result they will give you? Like age. You want to know the age. And they will let you know this is numerical variable, and the range of age variable is from 0 to 85. And they have 82 unique values. Okay, so not 85. So some number is missing in the age. And they're going to give you some example. And also they let you know any missing in the data set. No, 0. Okay. This is so you can do this by yourself. So if you implement codebook, they will show all the variables. Okay. And sometimes we call summarize. It's quite useful command for this data. It can provide summary statistics for specific variables. So again, you type sum or summarize. It's either way. Sum, the variable name, it will generate the summary statistics for these variables. Okay? And you can also put the option D that give you more detailed information about this variable. And if you do not put anything, you will give you all the variables. Okay. So here I just give you some example. So if you implement the sum, it will let you know what's the mean of that variable, what's the standard error of that variable, and maximum value for this variable. And you can, but if you put a detail, D here, it will give you more information about that variable. For example, what's the median, the 50% percentile of that variable, 99% percentile of that variable, and variance, skewness, something like this. That's something you can, you will get. Okay. Okay. Any question for this? And another command called tab can help you to produce frequency table. That's useful for if your data is a categorical variable. This is for the can consider for continuous variable. So tab again, you put tab. The variable you want to explore. For example, you tap age. This will give you the result looks like this. The 1 year old, how many observations you had, and the share of the observation with 1 years old. Okay. Okay. And if you type 2 variable, that will give you their interaction. So that is the result looks like this. The age 1, if you are male, how many observations? Age 2, age 1, if they are female, how many observations? So they will looks like the result looks like this. Okay. And the tab can combine with summarize. It will give you each gender's average wage. Okay. So if you do this, it will like this. You tap the gender, male and female, and summarize this variable. So basically, it will generate the output like if you are male, the average wage, female average wage, and the total. Okay. This is something you can practice. And inspect is another command that can show up the distribution of the variable. For example, again, very simple. Say inspect the variable name, inspect the wage. And this will give you some result looks like this, the age distribution, and it will let you know how many observation with 0 age, 600, and positive and negative. So for age, it should be no negative value. So if there's not something happen here, you might find that your data might have some problem. So this can help you to check an integer or non-integer. Okay. Okay. Finally, I would like to introduce 2 important commands that can help you to check whether your observation can be uniquely identified by specific variable. Okay, that's quite important because we don't want our data set have exactly the same observation. What is exactly the same observation? That means the observation share the same value of characteristics in terms of all variables. Then, if there's no reason, you shouldn't drop some of this variable, this observation, because these observations do not give you extra information. Okay, because all the variables are the same. Okay, so you can use ISID and duplicate to explore such issue. So ISID, again, very simple. You just type this, and the variable you want to check is basically check whether this variable can uniquely identify specific observations. So this variable in our data set is household number. Okay. So you can consider one household will have one number for this variable. But our data set is individual level data. So maybe one household might have 3 individuals. So these 3 individuals will have the same serial numbers. So basically in our data set, serial number, this variable cannot uniquely identify one observation because our data set is individual level, not household level. Okay. So if you implement this, so what is serial number is here. This is serial number. This is household ID. So this is the first household. So the first 5 individuals belong to the same household. Okay, so they all have the same household ID. So this variable cannot uniquely identify. So if you use ISID, they will let you know it cannot uniquely identify. Okay, but maybe you have another variable that can uniquely identify individual. For example, individual ID that should be individual identified. But if you find the individual ID cannot uniquely identify observation, that means your data have some problem. That means 2 individuals share the same ID. That could be wrong. And you can use this to check.
So do you mean every table has to have at least one unique identifier?
Whether they provide such information to you, it depends on the data you use. Typically, a good data source will give you individual identifier. But that means each observation or each household, each individual will assign one unique number.
So even if it doesn't have a unique identifier, it wouldn't be a big problem, or would it?
It depends on your data. If your data is panel data, that's not a problem because you basically follow the same individual over time. So that means the individual ID will show up several times in your data set. So that's not a problem. But if your data, you kind of know one individual ID, one ID should correspond to one individual, but you use this command and check they are not uniquely identified observation, you should pay attention. And how to detect the extra observation, you can use the following command that I will let you know is called duplicate. This can help you to detect repeat observation in terms of the variable you specify. Okay. For example, there are duplicate and you can type several options here. Okay, so you can help. So if you want to learn more about this data, you can help duplicate. And they will let you know how to use it. And this can let you know, duplicate, you can have some option and put the variable name and you can put if or something. And there are other options, give some example or list. and we will discuss later. Okay. Okay, for example, if you report means they just give you the table to let you know how many observations are repeated. For example, this is serial number, that is household number. So you will expect it will repeat several times because our data set is individual level. So this means around 5,000 observation has unique household ID. So there's no surplus, 0. And around 13,000 observation, they have 2 clones, kind of like 2 copies. So that means this observation has two observations shared with the same household ID. Okay, so this means half of them actually have repeat household ID. And 3 means 3 observations share 1 household ID. And such observation we have 11,000. So around 2/3 are have repeat. Okay, so only 1/3 have maybe if you want to just keep 1 household ID per observation, you just need to just keep 1/3 of observation. Okay. Okay. And if you do not specify any variable, it will check whether your observation has the same value of all the variable. So usually, if your data is correct, there should be uniquely identified in terms of all variable. Okay. So typically, it will be 1 copy for all variable if you in terms of all variable. If not, it's possible your data have some problem, because that means some observation, 1 observation, 2 observations share the same value of all variables. That's very strange. Okay. Okay. Finally, I'll give you several options you can use, like duplicate example. So basically, they will give some example in terms of this duplication, and will give the list of the sample for these duplications. Okay. So what this means is if you use example, they will give you. You want to know whether the observation share the same household ID and age and year, and this give you some example. The observation 17, observation 25, they have duplicate. Okay. But if you put the list, this just give you 1 example for each typical case. But if you put the list, it will give you complete list of such duplication. Complete list for those who have the same serial number, age, and year. For example, observation 17, observation 19, they have the same serial number, the same age, the same year. So you can check, you can detect this. Okay. Okay, and finally, you can use another option called tag. It will generate a new variable that let you know how many repeat observations you have for specific observations. And you can also use this option called drop to drop all the repeat observation in terms of this variable. Okay. And sometimes they may not let you do that because dropping some variables, dropping some observation could be not good things. So you can look, if they do not allow you, you can type the false to make they directly drop. Okay. So just let you know, you can type drop. So originally the data set is 60,000 and it's individual level data. Okay. But now we want to keep just one observation per household. So we can use duplicate drop based on household ID. So that will drop only one household ID. The one household ID only have one observation. So if you do that, they will make the data looks like this. One household ID, only one left. So the first observation will be keep. So any questions? Okay, actually I record a video for the data part, but it's not record what I discuss now. I record using other time. So it's discuss the same material, but it's not exactly the same what I just teach. So that's came for you a review by yourself. Yeah, but I know I go through very quickly, so I record a video for you to learn this. Okay. Okay. So any questions?
So where is the video?
I will upload. I just finished yesterday. Yeah. Okay. So the next week we will move to discuss the third education strategy is the regression and machine learning. So how to apply machine learning to the causal inference. Okay.
So professor, so I guess like a general, like when you first start, what's the best way, like when you first start data, because like you know how there's that one thing.
One thing is you need to change the path.
Oh yeah. Or I've not like I already changed the path on it. So my question is kind of like is it best to just click on the do file or should you open the do file later?
的话就是这个是一个 serial 对 open the new file and highlight the code.
Okay, so you open data by clicking on then like you highlight this and then you
click here.
So that's how you're supposed to start.
Yeah.
And then
write everything, write every command. 对，一设计它一设计它只有 permanent you have everything. 代表刚刚说的是
so you shouldn't really do command.
Yeah, I do like this. But you do this next time, you should repeat again. Rest of the time. If you stop here, you can just highlight.
What if you just want to run the whole thing? You just highlight the whole thing and run,
or you don't highlight, just press.
Okay.
我是水母。可以跑，那个真跑。吃晚餐。越看越惨。就是类似7点钟那个管理。我决定钱啊，后来发现我没有钱。
我以为你是在
那你第二部分没有在前面样本能播放能力和差别，对于艺术类型的收的方式。
如果你去公园去做一些其实也是有关的事，说因为 match 女的她比较把握，所以其实某个程度，你可以从这个分析来预测，其实疫情对女的影响很奇怪。
Are you taking a class tomorrow? Are you taking This game?
Yeah.
Yes.
Sorry.
Yeah, I'm not taking. Yeah, I'm not taking.
I was thinking that you're taking the gig economy.
I would have, but then I was like,
You wanted to be prior to the gig.
well, I'll need it for work because I want to work as a data scientist.
对对，第一个是这样，就是不同
We'll come on Friday. Let's use
不同
workshop.
县市
I don't know if I need to now since I have my advisor.
Who?
Professor Joanichi.
Oh, 张一起. Oh, you find
疫情对不同的
Yeah,
不
he
同
used to be my
不
maker
同
professor
的
here,
的
so in undergrad. So I was like, okay, because I feel
但因为
like
你前
my
面已经建立一
topic
个
is
关系，就是
related.
说
Plus, I know he's going to
谁
speak
都
with
会帮他们比较好，所以其实
But it's very
后
strict.
面
So remember
的
in
话
human
其实
capital.
大概就可以预期。
I know I took that class.
Yeah.
So I mean that as an advisor instructor, how was it?
理论上
I
我
well,
也不知道。
I'm scared because it's very strict and it's very busy.
Yeah.
It publishes like a lot. So I feel like I don't want to waste his time. Like whenever we have like a meeting, because we have like a meeting tomorrow, I want to be like prepared all the time.
对。
So
加油. But do you know that you should print something
yes,
and
to get into
it
science. Yes. That's really
对对对对对。
But
或者是
another
他
one,
他
like
最
I
高
know that after the meeting,
有一
I
些人
get an
播放
advisor
能
before
力
the meeting.
好的，播放能力高
A lot
跟
of
低
people
的
are
比
gonna
较
wanna
你
start
主要
because
是
there'll be a lot of competition
因为
after
那
that.
个你在算你的
So start emailing now.
根据他自己的
Your email your first
这
choice now. If
个
your，first
所以
choice
你
is
其
like,
实在
oh,
比
too
就
busy,
是
then
播
email your
放
second
控
I
能
know, I
力
know.
比较好的
Well,
是
I
怎
have
么样
a
的？
I do know.
相较于播放能力比较差的
Oh,
人
you rock. Oh, that's a good
他
choice.
们在疫情后心
Bye.
变化比较小，或者是有比方有成长。对，你其实看就是对这个，所以你的核心是播放控。
他很硬，非常
对，播放还有疫情。
对
对对，所以其实你文献回顾，对我就会觉得你第一部分其实就是跟其他国家播防控的状况是怎么样，还有什么是播防控。播防也是一个蛮新的概念，可以讲一下，因为疫情。然后第二个可能有关文献就是疫情怎么影响到劳动市场，特别是有没有人真的就是在看你真的在做的东西，就是疫情如何因为我防控能力不一样的人，对我防控能力不一样的人造成的影响是什么？其实有可能有一些文献在看的时候，疫情对女生、男生影响，或者是对什么样子影响，其实他们可能都可以归咎于我防控能力不同而有不同，可能，但也有可能跟我防控没有关，也有可能。对。
因为台湾的文献真的很少，
对对对，
都是比较偏人资去看。
对你不用真的没有不用放，就不要放真的没关系，只是因为它是台湾，因为有可能你是第一个做的，对，所以而且可能国外也不多，所以你就是放有的，有关的，真的蛮有关的，那也真的很少就不用硬放，对，但是不要放过很有关的，好吧？就是要多只好就好，量不用多。好，因为有可能这真的很新。台湾可能你真的是第一个讲这个，这么新的议题。
对，但是那时候想说，感觉有这些资料去做，其实不会到那么难。
对对，
确实是在找一些相关去参考的东西会很少。
对，可能比较多，有可能是国外，但是就是文献就是跟你的主题有擦边，就是有当然也要蛮有关，但是不是完全一模一样这样子。对对。那我的感觉就是，work from home 应该是一个，还有那个疫情。但是这疫情就是疫情怎么影响劳动市场？啊，work from home 就是这个文献就是一个新的概念，然后它跟它有关的可以讲一讲。但是可能大概要讲的会是，就是哪些国家或防控的指标、这个能力，还有产业过去怎么讨论这个，
所以是要找，
或者什么样职业是我防控能力比较好。其实你可以去 follow 看看那一篇算那个我防控指数的文章，因 因为可能会有人也是像你一样用他们算出来的指数去做其他国家防控的能力。这一些文章就是跟你们有关。
好，
对
好，
对。
有那时候
你知道怎么去看那种 citation 吗？
就是他们最下面会有那个一些。
对，就是 Google 的 Google。我忘记这个文章。
哦，他叫那个 how many。
对，你稍微打一下。我后面这么有名。我好像被引用1000多次，好恐怖。对，你可以这样做。这个研究生也确实可以了解 Scholar，Google Scholar 这个网站，然后你关发文，然后放在这边，然后它就会产生嘛1000多，然后但是它跟刚刚的不一样，是你可以去看到底是谁在用，然后你可以去定说，搜寻引用以下内容，然后你可以定说几年到几年，就是你想看非常非常细，它就会跟你讲哪一些文章，就是你可以看一下台湾人用它，台湾就是说有没有人引用这篇文，那有的话就可能很有关 ，impact of Japanese。不过这里到底有没有关，也是看你的判断。我觉得可能就是可能也很多没有什么关。对，但是就大概就是可以这样子找。
那个就是因为我们这边有限制要几字或是几页吗？
没有。
没有。
我没有，我知道的我不太限制。
因为我那
就是你就是写的。
因为很多人他们都是在文献这边会讨论很多，然后就是。
不用，就是你就是要讨论有关的就好。对。
好。
重质不重量，不用很多页。
对，但我现在有时候如果之后有更新，我通常会写多一点，是我有想说就是尽量详细，然后要删还可以。
对，这是一个好方法。
所以我写的时候会可能写的详细。
对，可以啊，可以。不会。不会，拜拜。